Hello everyone. 12 PostgreSQL internals every senior DBA must understand. For Oracle DBAs moving to PostgreSQL and PostgreSQL DBAs who want to operate at senior level. Deep concept that decide performance, stability and correctness in production. PostgreSQL is not just queries and indexes. If you are an Oracle DBA moving to PostgreSQL or a PostgreSQL DBA who wants to operate at the senior level, the single biggest gap is misunderstanding the internals. The deep concept that decide whether your database is fast, stable, and correct under production load. Today we are covering all 12 of them. Every concept has a real world impact, a monitoring query you can run right now, and where relevant, a comparison to what Oracle DBAs already know. Alright. So that agenda 12 PostgreSQL internal complete coverage in this video. Number 1, MVCC versions not overrides. Number 2, WAL real source of durability. Number 3, checkpoints, hidden IO storm. Number 4, Autovacuum, lifeline not cleanup. Number 5, visibility map, secret behind iOS. Number 6, hot updates, no index cost. Number 7, replication slots, WAL killers. Number 8, X-Wind horizon, cleanup blocker. Number 9, red frozen anxiety, Wraparound bump. Number 10, bloat, invisible thief. Number 11, buffer cache, memory equal to performance. Number 12, failover reality, replica ready. And daily monitoring dashboard and key takeaways. So this is AA DBA Hub, your Oracle DBA Knowledge Hub. I am your host Ramesh, and hit subscribe and let's go into the deep dive. Okay, so first, number 1, MVCC version not overrides. Let's go for the overview how the 12 internals connect. The MVCC, every update creates a new row. Dead row must be cleaned up by vacuum, foundation and everything else. WAL, write ahead log, source of crash recovery, PITR and streaming replication. Checkpoints, flush dirty buffers to disk, bad tuning equal to IO spikes, good tuning equal to smooth performance. Auto vacuum, remove dead tubules, prevents bloat, freezes anxieties, updates statistics, critical infrastructure. Visibility map, enable index only scans, vacuum sets bits must be current for iOS to work. Hard updates, updates that skips indexes modification, huge writer savings or high update tables. Replication slots, silent WA killers, inactive slots plus no monitoring equal to disk full equal to crash. X-Wind horizon, oldest active anxiety, blocks vacuum from removing dead tuples, idle transaction or poison. Wraparound, run frozen ID, anxiety age equal to be equal to read only mode, monitor age daily, vacuum freeze is the fix. Bloat, dead tuples plus outdated indexes equal to invisible performance degradation, detect and remediate. Buffer cache, shared buffer is everything, hit ratio target greater than 99%, miss equal to disk IO equal to slow queries. Failover reality, streaming is not equal to failover ready, validate lag, test failover, don't assume it works. Okay, number 1, MVCC version not overrides. The most fundamental differences from the Oracle The Oracle DBAs know MVCC, but PostgreSQL implementation is a fundamentally different. When PostgreSQL does an update, it never overwrites the original row. It creates a brand new row version in the heap. The old version stays there, both exist simultaneously. Oracle stores old version in undo table space and releases them when the transaction commits. PostgreSQL stores old version inline in the heap and they can only be removed by vacuum. This is the foundation of everything else. Every concept we covered today connect back to this. PostgreSQL keeps dead rows in a table and managing those dead rows in a DBA's most critical responsibility. Monitor with select PID, age, backend and XID state from PG underscore state underscore activity. This is show you how old each transaction view the vals is. Okay. So here is the scenario. The PostgreSQL never overwrites a row. Every update creates a new physical row version in a heap. Old version stay until vacuum removes that. So here is that update employee salary where equal to employee in 101 in heap store the after update. So this is that method that MVCC version not overrides. Okay. Oracle mental model old version stored undo table space released after transaction commits undo space auto managed. PostgreSQL mental model old version stored inline in the heap not released until vacuum runs. This is why vacuum is critical infrastructure in PostgreSQL. Okay, let's move to monitoring, MVCC monitoring and real world impact. You can monitor this through this query. And the real world problem, a long running ideal in transaction session holds and old XID snapshot, all dead tuples created after that XID snapshot cannot be removed by vacuum. Even if auto vacuum runs perfectly, this causes unbounded bloat. So the fix, set idle underscore in underscore transaction underscore session underscore timeout equal to 5 minutes in PostgreSQL.conf file kills idle transaction automatically. This is the real world problem, right? So this is the fix also. You need to configure in the PostgreSQL conf file to this parameter need to set 5 minutes, whatever you want, 10 minutes, 15 minutes like that. So the kills idle transaction automatically. So number 2, WL, the val lags, right? The real source of durability. Oracle DBAs know redo logs. PostgreSQL WAL is the same concept. Data is written to val before it returned to the data files. That commit is considered complete when val is flushed to disk, not when data files are updated. Val powers 3 critical features: crash recovery, point in time recovery, and streaming replication. Every one of them depends on the val being healthy. Monitor with pg underscore current underscore val underscore lsn, pg underscore stat underscore val, and pg underscore stat underscore replication. Watch val generation rate. A sudden spike in val means your write workload has changed or something unexpected is updating large amount of data. So there is a huge workload happens, then there will be some spike in the val means. Okay. So Oracle DBAs know redo log. Val is the same principle, different implementation. Commit is issued, application sends commit and command to PostgreSQL. Val record written XID LSN before image, after image recorded in val buffer. Val flushed into disk. Val writer flushes val buffer to val files on disk. Commit complete. Here not when data files are written. Data files are updated, async later. So this happened, crash recovery, replay val from lost checkpoint and startup, database consistent even after hard crash. Point in time recovery. Point in time recovery, replay val to any specific timestamp, recover base backup plus val archives. So streaming replication, val records shipped to standby in real time, replication applies val continuously, source or for all replication. All right. So the monitoring, well, monitoring queries, you can monitor through these queries. Select pg underscore current underscore val and LSN as a current LSN, and pg underscore stat underscore val, and pg underscore ls underscore val there, and pg underscore stat underscore replication. You can monitor using this val current utilization, usage, and everything else, right? So Oracle term readlog LGWR in Postgres is equivalent val writer process. DBWR, the BG writer plus checkpointer, log switch, while segment rotation, SCN system change number, LSN log sequence number. Here is that Oracle term and PostgreSQL equivalent term, right? So next, so number 3, checkpoints the hidden IO stock. Checkpoints flush dirty buffers from shared buffers to data files. They are necessary, but badly tuned checkpoints cause latency spikes that look like misty slowdowns to the application team. The two failures modes are too frequent constant IO pressure, low throughput, too rare long recovery time after a crash. The fix is in 3 parameters: max underscore val underscore size, checkpoint underscore timeout, and checkpoint underscore completion underscore target. Set max underscore val underscore size to 4 GB, checkpoint underscore timeout to 10 to 15 minutes, and checkpoint underscore completion underscore target equal to 0.9. That spreads the IO over 90% of that interval between checkpoints, eliminating the spike. Monitoring through that PG underscore state and BG writer, if you are seeing checkpoints underscore records higher than checkpoints underscore timed, your val is filling up before the scheduled checkpoints. Increase max underscore val underscore size. All right. So the checkpoint flush all dirty shared buffers to disk necessary for crash recovery, but poorly tuned checkpoint cause latency spike. Too frequent checkpoint, constant IO pressure on storage, low throughput through the checkpoint burst, application queries interrupt by IO spikes, cause max underscore val underscore size is too small. Too rare checkpoint, long crash recovery time, replace more val, risk slow startup after crash. SLA impact during unplanned outages, cause max underscore val underscore size is too large. Alright, so you can monitor using the checkpoint health using this query from PG underscore stat underscore BG writer. But one small warning here: the buffers underscore backend greater than 0 means application sessions are directly writing dirty buffers. PG writer can't keep up. Increase BG underscore writers LRU underscore max pages or review shared underscore buffer size. Alright. So the checkpoint tuning, the key parameters here. So you need to configure in the PostgreSQL.conf file. Optimal checkpoint configuration, max underscore val size 4 GB, min underscore val size 1 GB, checkpoint timeouts 10 minutes, checkpoint completion target 0.9. So BG writer tuning process, write dirty buffer pages proactively. BG writer underscore LRU underscore max pages 200, BG writer underscore LRU underscore multiplier equal to 4.0, BG writers underscore delay equal to 100 ms. So production scenario fix, users reports 30-second slowdown every 5 minutes, checkpoint underscore requires greater than checkpoint underscore timed, while filling before scheduled. What is the fix? The increase max underscore val size to 4 GB. Sets checkpoint underscore completion time 0.9. Latency spikes eliminated here. So healthy checkpoint metrics, checkpoint underscore rex greater than slash total less than or 10%, checkpoint underscore write underscore time less than 30 seconds, buffer underscore backend equal to 0, max return underscore clean equal to 0. So warning signs, checkpoint underscore requires greater than checkpoint underscore timed, buffers underscore backend consistently greater than 0, checkpoint underscore async underscore time equal to spikes. Okay, so this is checkpoint tuning, the key parameters. So number 4, Autovacuum lifeline, not a cleanup job. Autovacuum is a critical infrastructure. If it is falls behind, the bloat accumulates, plants degrade, wraparound production triggers. Okay, this is the most misunderstood process in PostgreSQL. Oracle DBAs often think of it like Oracle online maintenance jobs, something that runs in the background and it isn't critical. That mental model will get into you to serious trouble. Autovacuum does four things: removes dead tables, prevents bloat, freezes old transaction IDs to prevent wraparound, and updates statistics for the query planner. If Autovacuum falls behind, you get bloat, you get bad execution plan from the stale statistics, and eventually you get a table level wraparound production, which puts a table into the read-only mode. Monitor p underscore state underscore all underscore table. Look at n underscore dead and tube underscore last underscore auto vacuum. If your tables have high dead tuple counts and the last auto vacuum was yesterday, the auto vacuum is struggling. Tune auto vacuum underscore vacuum scale factor down to 0.01 and increase auto vacuum vacuum underscore cost underscore limit to 400. So it is remove the tuples, clean dead rows from the MVCC updates and deletes, reclaim space for reuse, prevent bloat. Regular vacuum keeps table in size in check. Without it, tables grow when the row count is stable. Freeze old XIDs. Prevent a transaction XID wraparound and the database goes read only if this is fails. Update statistics. Keeps query planner statistics fresh. Stale states equal to bad execution plan equal to slow queries. So the consequences of auto vacuum falling behind. Number one, bloat. Dead tables accumulate, tables grow, IO increases. Number two, wraparound risk. XID wraparound causes read-only database shutdown. Number three, plan degradation. Stale state statistics equal to bad plans equal to slow queries. So none of these have obvious error message. They are silent killers of your database. Okay. Okay, let's move on to auto vacuum monitoring tuning. So this is that table and auto vacuum is struggling. You can monitor through through this PG underscore state and all underscore table views, and watch currently running auto vacuum workers. You can monitor through that PG underscore status in progress under vacuum. You can monitoring through this SQL queries. So you need to configure global tuning PostgreSQL conf file auto underscore vacuum underscore scale factor equal to 0.01, auto vacuum underscore analyze underscore scale underscore factor equal to 0.005, auto vacuum underscore cost underscore limit equal to 400, auto vacuum underscore cost underscore delay equal to 2. So per table override, alter table hot table set auto vacuum underscore scale underscore factor equal to 0.01, comma auto vacuum underscore cost underscore limit equal to 800. So per table override. Alright, so this is what auto vacuum can be monitored through the tuning. And next, number 5, visibility map, the secret behind index only scans. The visibility map is a bitmap with 1 bit per heap page. When the bit is set, it means all tuples on that page are visible to all the transaction. So no heap fetch needed for index only scans. Vacuum sets these bits. If auto vacuum is behind, the bits aren't set and index only scans degrade into heap scan 3 to 10 times slower on large table. Okay. So the visibility map is a bitmap with 1 bit per heap page. Bit equal to 1 means all tuples on that page are visible to all transactions. Enable index only scans without heap access. So you can monitor the index only scan effectively. You can use the pg underscore status and user underscore tables and check VM status of the page. Inspect records extension. You can use the pg underscore visibility. So these are all the views. You can use it for the monitoring purpose. Vacuum sets VM bits. If auto vacuum is behind, VM bits aren't set. Index only scans is become heap scan 3 to 10x slower. This is why vacuum is IO's performance are directly linked. Right? So number 6, hot update without index cost. Hot heap only tuple updates occurs when the update does not change any indexed column. PostgreSQL creates the new row on the same page. No index modification needed. When you update a row and don't change any indexed column, PostgreSQL cannot do a hot heap only table update. It creates the new version of the same heap page and changes into that old version. No index modification needed. This serves enormous write amplification on a high update tables. Monitor n underscore tube underscore hot underscore UPD divided by n underscore tube underscore UPD in page underscore state underscore user underscore tables. A hot percentage above 80% means your schema design is working with the PostgreSQL internals. Below 20% and percentage means, and you should ask whether all those indexes are actually needed. All right. So the regular update indexed column changed, new row created, old row marked dead, index pointer must be updated, new location, high write amplification, every index and the table gets updated. Hot update, non-indexed column changed, new row created on same page, old row changed to new row, index not updated, still points to hot chain, zero index write amplification. So monitor using this query, hot update, you can from the page underscore status and use underscore tables. Target hot percentage greater than 80, well-designed schema working with PostgreSQL internals. Hot percentage less than 20%, ask whether all those indexes are actually needed. Consider fill factor equal to 70 for high update tables. All right. So replica slots, silent val killers. Number 7. This is one causes the most production disaster I see. Replication slots are prevent val from being deleted until a replica consume it. That's the feature. But if a replica goes down and no one notices, val accumulates indefinitely until the disk fills up and PostgreSQL crashes. I have seen this cause complete database outages over a weekend when a replica went down on Friday and no one was monitored val retention. The monitoring query you need to run daily, select slat underscore name, active, pg underscore size pretty, pg underscore val lsn diff, pg underscore current val lsn, restart underscore lsn as a retained underscore val from pg underscore replication underscore class. Set up an alert if retained val exceed 10 GB and in PostgreSQL 13 and later version, set max underscore slat underscore val underscore keep underscore size. This caps how much val a slot can retain before PostgreSQL invalidates the slat rather than running out of disk. Okay. So the PostgreSQL replication slot retain val until replica consume it. If replica goes down and no one notices, val accumulates until the disk fills and PostgreSQL DBAs crashes. So number 1, replica connects, creates replication slot, PostgreSQL mark restart underscore lsn. Number 2, val is generated continuously on primary, slot prevents deletion. Number 3, replica goes offline, slots become inactive, no one consumes val. Number 4, val accumulates unbounded gigabytes per hour on the busy system. Number 5, disk consumption full, PostgreSQL crashes, complete outage. So the real disaster, replica went down Friday, team thought it was temporary. By Monday, 847 GB val had accumulated, primary disk full, PostgreSQL crashed, complete outage on Monday morning. Okay. So replica slot, you can monitor using this query. Daily monitoring SQL, run this daily to monitoring that too much slot remaining, too much val required. So using this pg underscore replication and slots view, you can through fire this query. At safety limit, PostgreSQL 13 place, prevent unbounded growth, alter system set, max underscore slat underscore val underscore keep size equal to 10 GB, select pg underscore roll under conf. So drop an inactive slots, verify replica is truly decommissioned first, select pg underscore drop and replication underscore slat underscore name here. Okay. So this is what we can monitor daily on the replication slot. Alert threshold, set monitoring alert If any slot remains greater than 10 GB of val, this gives you the time of investigate before disk fills. As always, the best practice is set max underscore slot underscore val underscore keep underscore size equal to 10G in PostgreSQL 13 plus. Also monitor active column, inactive slots with large retained val equal to immediate action required. Alright. So number 8, X min horizon, why vacuum can't clean what you think it should do. Okay. The X min horizon cleanup depends on it. The X min horizon is the oldest active transaction XID in the database. Vacuum cannot remove any tuple newer than this horizon. The X min horizon is the oldest active transaction XID in the database. Vacuum cannot remove any tuple newer than this horizon, even if the application committed that transaction hours ago. The most common cause idle in transaction connection. An application session starts a transaction, reads some data and never commits or rolls back. It just sits there. The session holds the X min horizon back, blocking vacuum from cleaning millions of dead tuples. What is the fix? Set idle underscore in underscore transaction underscore session underscore timeout equal to 5 minutes in PostgreSQL.conf file. This automatically kills the session that hold a transaction open without doing anything. Right? So you can monitor that query pg underscore state underscore activity. This way you can monitor. So idle transactions are the most dangerous. From pg underscore state and activity, you can monitor the idle transaction. The worst case, connection pool opens transaction, reads data, never commits. Those connections hold X min horizon back in hours. Vacuum runs, finds millions of dead tuples, removes 0 because all are newer than the X min horizon. What is a fix? You can fix auto system set idle underscore in underscore transaction underscore session underscore timeout equal to 5 minutes and statement underscore timeout equal to 30 minutes in PostgreSQL file. Alright. Number 9, rel frozen XID. The wraparound time bomb. Okay. Every table has a rel frozen XID. The transactions are consumed. The age increases at approximately 2 billion XIDs. PostgreSQL forces read-only mode to prevent corruption. The transaction IDs are PostgreSQL are 32-bit integers. They wrap around at 2 billion. PostgreSQL tracks how old each table transaction IDs are using. Rel frozen XID, when the age approaches 2 billion, the PostgreSQL forces the database into read-only mode to prevent corruption. So monitor age rel frozen XID in pg underscore class, alert when any table XID's age exceed 1.5 billion, run vacuum freeze immediately. If Autovacuum is healthy, you should never get close to this threshold, but always monitor it. Alright. So you can monitor the rel frozen XID age for tables using this pg underscore state underscore all underscore table views. The database level frozen XID age from pg underscore database. Save zone. XID age less than 500 million, Autovacuum running healthy, no action needed. Warning zone. XID age 500 million, approximately 2 million to approximately 1.1 billion, increase Autovacuum aggressiveness, schedule vacuum freeze. Danger zone. XID age greater than 1.5 billion, run vacuum freeze immediately. PostgreSQL will force read only at 2 billion by automatically. Okay. So this is a warning danger zone. So we need to run vacuum freeze immediately. So wraparound key parameters and emergency response. The key auto vacuum freeze parameters in the PostgreSQL .conf file. Auto vacuum freeze underscore max is 2 billion. Vacuum freeze min age 500. 2 billion and 500 million. Vacuum freeze table age 1.5 billion, right? So it is trigger freeze at 200 million XID age. Don't freeze very recent rows. Freeze aggressive at 150 million age. Okay. So emergency scenario, run aggressive vacuum immediately. Vacuum freeze verbose your oldest table. Emergency scenario, increase auto vacuum aggressively temporarily, alter system set you need to increase accordingly. Select PG load conf file. So how long until wraparound production kicks? So it is kicks 2 billion, right? From PG underscore database, you can mount. So Oracle DBA analogy, Oracle prevent XID equivalent wraparound without automatic SCN management. PostgreSQL requires active DBA monitoring of XID age. If Autovacuum is healthy and monitored, you should never get close to 2 billion, right? So this is one of the most important critical key parameter and emergency scenario. Number 10, bloat the invisible performance thief. The dead tables and outdated indexes waste space, increase IO, inflate backup size, and pollute the buffer cache, all without any obvious error message. Dead tables and outdated indexes waste space, slow everything down. The problem is invisible. The application sees slow queries, but the table sizes looks normal on the file system. So you can monitor with the pg underscore state and the user underscore table. Look at n underscore 10 to tube underscore tube. A percentage of n underscore live underscore tube. Install pg startup for a more accurate bloat analysis. For the remediation, standard vacuum reclaim space for reuse and doesn't return it to the OS. Vacuum full rewrites the table and return disk space, but lakes the table, re-index, concurrently rebuild the indexes without locking the PostgreSQL 12 and later. Consider setting fill factor to 70 and the high update tables. This is reserves 30% of each page for hard updates. So you can monitor the find bloated tables quickly using the pg state and the user underscore table and find unused potentially bloated indexes, pg underscore state user underscore indexes. These two views you can monitor it, right? The bloat remediation, the right tool for each situation. Option 1, standard vacuum non-blocking reclaims reuse, vacuum verbose orders, online, no lab, does not return to disk space to OS. Option 2, vacuum full, rewrites table, return to disk. Vacuum full orders, return to disk space, logs table, use in maintenance window only. Option 3, reindex concurrently, PostgreSQL 12 plus versions. Reindex concurrently orders underscore customer underscore IDX, online rebuild, no log on read writes. Option 4, pg underscore repack, online table rewrite extension. Pg underscore repack, table orders, rewrites table online, return space, best for VLDB. Prevention, fill factor leaves room for hard update. Alter table, high underscore update underscore table set, fill factor go to 70%. The resource 30% of the each page of hard update reduces the bloat rate, right? So the Oracle equivalent, Oracle segments string and DBMS redefinition equal to PostgreSQL vacuum full slash PG and repack. Oracle does the things online via row movement, PostgreSQL vacuum full logs. Use PG repack to zero downtime bloat removal, right? So this is a remediation for bloat remediation. Number 11, buffer cache memories of performance. PostgreSQL reads pages into shared underscore buffer, cache get equal to nanoseconds, cache miss equal to disk IO equal to millisecond. Hit ratio is the most important memory metrics. So every query goes through the shared underscore buffer, a hit underscore nanosecond, and miss means disk IO equal to millisecond. Your target hit ratio for an OLTP workload is 99% or higher. Monitor the hit ratio with the query against the pg underscore stat IO underscore user underscore table, sum heap underscore blocks underscore hit divided with some sum of hits plus reads. If your hit ratio is below 95%, you need to more shared underscore buffer. Or your working set is larger than available memory and you need to investigate caching strategy. Shared underscore buffer should be 25% on system RAM as the starting point, but always benchmark you have to your specific workload. All right. So you need to monitor the overall buffer hit ratio 99 greater than 99% in this query from PG state user tables and per table hit ratio from PG state database. All right. So buffer cache tuning and Oracle comparison. So key memory parameters in PostgreSQL, shared underscore buffer 8 GB, 25% RAM starting point. Effective cache is size to 24 GB. Estimate of total cache size OS plus PG. Work underscore memory 64 GB per shot. Has careful with the connection. Maintenance work memory equal to 1 GB. For vacuum, reindex, create index. Alright. For Oracle and PostgreSQL perspective, Oracle buffer cache, DB underscore cache and size. In PostgreSQL, shared underscore buffers. In B cache buffer headers, in PG buffer cache extension. B systate buffer get ratio, PG states IO user tables. Large pool, work underscore mem processor. PG aggregate target, work mem into max underscore connection. Keep recycle pool, PG pre-warm extension. So work underscore mem warning, work mem underscore is mem is a per operation, not per connection. If under connection each run sort that uses work underscore mem equal to 64 MB, that is 66.4 GB of memory, that is just for sorting. Sets conservatively and increase per session when needed. Alright. Number 12, failover reality replica does not equal ready. A streaming replica that shows the connected is not necessarily ready for a clean failover. 4 conditions can make a running replica unsafe to promote. This is most dangerous assumption in PostgreSQL production environment. A replica can show a streaming and connected but still not be ready for a clean failover. 4 things that can make a running replica unsafe. Replication lag, that replication is behind the primary val apply lag, that replica has received val but hasn't applied yet. Long running transaction on primary that haven't replicated, unreplied val sitting on the replica services and buffer. Monitor page underscore state underscore replication from the primary. Check write underscore lag, flush underscore lag and replay underscore lag. All should be near 0 for healthy failover candidates. Before any planned failover, run a complete validation. Check replication lag, verify no prepared transaction, confirm the replica, report PG underscore is underscore in underscore require true, and verify the received LSN matches the replayed LSN. And most importantly, the test your failover. Don't assume it will work. Schedule a quarterly drill. The worst time to discover your replica isn't failover ready is during your actual outage. Okay, so there is replication lag. Replica is seconds or minutes. Begin primary promotion equal to data loss for that lag period. Val apply lag, replica received val but it hasn't applied yet. Buffer full equal to not updated with the primary. Long running transaction in primary may not have fully replicated to standby yet. Unreplayed val received but queued for replay. Promoting now equal to partial apply equal to inconsistency risk. So comprehensive failover readiness check, you can use this query PG underscore state underscore replication. So failover reality plus replica ready, right? So for failover readiness for pre-failover validation using the check 1 replication lag, PG state replication, check 2 no prepared in-doubt transaction, select count and PG and prepared in extraction exacts. And now check 3 confirm replica is recovery ready on the replica. You can use this the views. And check for monitor replication from the replication study. PG state val receiver. So the golden rule, test your failover. Don't assume it will work. Schedule a quarterly failover drill on a clone or a test environment. The worst time to discover your replication isn't ready during the actual outage. As a Oracle DBA note, Oracle Data Card has built-in gap detection, switchover validation, PostgreSQL record manual monitoring. It won't alert you if you are not failover ready, right? So there will be a huge gap from the Oracle Data Guard broker, Data Guard, and also PostgreSQL replication. So it is required manual monitoring, but Data Guard broker not required manual. It will detect automatically. We will fix the issue, right? All right. So those are the 12 PostgreSQL internal every senior DBA must understand. So the Oracle DBA to PostgreSQL mental model shift, concept Oracle Postgres, old row version, undo table space, inline heap vacuum, redo logging, redo log, LGWR, val, reval writer, dirty page plus, DB writer checkpoint, PG writer and plus checkpointer. Statistics collection, gather state jobs optional, auto vacuum critical. Time reference, SGN system change number, LSN log sequence number. Buffer cache, DB cache size, shared buffer 25% RAM, memory per query, PGA per session, work underscore mem per operation. HA replication, data guard, built-in verify, streaming manual monitoring. Online table rewrite, DBMS redefinition, PG repack extension. Wraparound production, automatic SGN, managed, manual monitoring recommended, right? So the daily monitoring dashboard, 12 critical queries. You need to follow this, and if you wish to take a snapshot also for this query for your future references. So daily monitoring dashboard, 12 critical queries. This is right. So what is the key takeaways? 12 internals, what every senior DBA must remember. MVCC, PostgreSQL never overrides rows. Vacuum is critical infrastructure. Old version stays inline heap until vacuum removes them. This is foundation for everything else. Well, the source of crash recovery, PITR and streaming replication. Commit completes after val, flushes no data file write, val health equal to database durability. Auto vacuum, if it is false begin, bloat, bad plans, wraparound, all silent. Tune scale factors, cost limits, monitor n and dead underscore tip underscore lost auto vacuum daily. Replication slots, monitor retained val daily, inactive slot equal to disk full equal to crash. Set max underscore slot underscore val underscore keep underscore say 10 GB, pre-G plus 13 plus, alert if any slot retained greater than 10 GB. Rel frozen ID, it's monitor the age daily, alert at 1.5 billion, vacuum freeze at 2 billion, too late. Auto vacuum handle this automatically, but only if it is healthy at the monitored. Failover, test it. Don't assume it streaming replica is failover ready. Validate lag, check report a transaction, confirm LSN alignment, test quarterly. Okay. So this is the know the internals respect the database and keep production safe. If this video helped you, please give it a like and really helps that AI DBA channel grow. Subscribe and hit the bell for weekly Oracle and PostgreSQL deep dives. Drop a comment with which of these 12 surprised you the most. I am curious what's new for Oracle DBAs moving to PostgreSQL. Find all the monitoring queries and scripts and under in my blog www.aidbahub.com. So this is your host Ramesh. See you in the next one. So the PostgreSQL is not just a queries and indexes. Internal decides a real world behavior and know the internals, respect the database, keep production safe. Okay. So I am going to post all the articles in my blog, DBA Hub, and the YouTube video. Next one, PostgreSQL auto vacuum tuning, PostgreSQL PITR setup, Oracle PostgreSQL migration. Already I posted. PG underscore status statement deep dive. So see you the next one. Thank you.